Hello and welcome to the introduction to Jaeger Talk. I'm Juan and this is Prithvi. We're both software engineers at Uber, the company that lost to Didi. And are they translating my jokes? Okay, whatever. And more importantly, we are maintainers of the Jaeger project. Okay, so as for the agenda, I'll do an introduction to distributed tracing to get everyone in the room familiarized with the problem area that Jaeger attempts to solve. Prithvi will then run in a demo of Jaeger and show how it can be used to debug certain observability issues within a microservices architecture. Then I'll give an introduction to the Jaeger project, talk about our project roadmap, and then we'll open the floor to questions. So before we get going, a quick show of hands. Who's familiar with distributed tracing and have used it at some point to debug a production problem? Okay, I count 3 hands. Okay, so cool. Okay, so for the newcomers, let's just go over the key concepts and terminology of distributed tracing to get everyone in the room on the same page. Okay, so why do we need distributed tracing in the first place? This colorful visualization is the service dependency diagram of a subset of microservices at Uber. So this means that every node in this graph is a service, and every edge between 2 services mean that those 2 services depend on each other. At Uber, we have over 4,000 microservices. This equates to more than 1 microservice per engineer, which is kind of stupid if you think about it. So as an engineer at Uber, how do you make sense of all this chaos? If you own one of the services in this diagram, and there's a problem with your service, how do you narrow down which one of your dependencies is actually the root cause of the problem? So distributed tracing can assist you with narrowing down your search space. Prithvi will be demoing this capability in a short while. So what else can distributed tracing be used for? So it can be used to monitor transactions in microservices. Let's say you have a transaction that is just isolated to a single service, like the diagram on the left. There are already existing tools to observe this transaction like this. You could use logging, for example. So if you do logging, when a transaction first starts, you can pass around the transaction ID and use it whenever you log something. You can then piece together the timeline for the distributed transaction via some processing by searching for all logs with that transaction ID. So this very simple mechanism will work for most both basic concurrency and asynchronous concurrency, as long as you add the ability to pass around this transaction ID throughout your code. However, once we move to a microservices architecture with distributed concurrency, simply passing around the transaction ID within a single service won't get you the entire picture. We now need a mechanism that can propagate this transaction ID across services, service boundaries, so that we can piece together the timeline of the distributed transaction. So distributed tracing solves this issue with context propagation. So what is context? Context is just some metadata that is passed around between services. This metadata includes a unique ID that can be used to identify the distributed transaction. On the left here, you can see a call graph where every node represents a service, and the directed edges between them signify a request. So service A receives a request from some external service, and it generates a unique ID and inserts it into a context object. The context is then propagated along to other requests. Okay, so the context is then propagated along with requests to other services. There we go. Here, service A calls service B. It will also include the context inside the payload. So to visualize the work done by individual services within this transaction, we use a trace view as seen on the right. Unlike the call graph on the left, where all we can see is the causality between the services, the trace view allows us to see both causality and the amount of work done by each service in the graph. So a trace is composed of multiple spans, and each span has a start time, a finish time, logs, tags, and represents the work done by a service within the distributed transaction. Here we can see that service A took the longest time to finish. We can also see that service A is calling service B, which in turn is calling service C. But then service B waits until service C is finished, and only then makes a request to service D, and so on and so forth. So one last thing I need to mention before the demo is that is OpenTracing. So you've probably heard about OpenTracing at this conference, since it's also a CNCF member project. It's a vendor-neutral instrumentation API that allows context propagation and distributed tracing, amongst other things. So as long as your services are instrumented with this API, you can plug in different OpenTracing compatible tracers like Jaeger, Lightstep, and Skywalking without having to rewrite all your instrumentation code. Okay, so I'll stop speaking now and let Prithvi do the demo.
Cool. Thank you, Owen, for that introduction. So I'm going to reconfigure my laptop, and we're going to do a quick demo. Hold on. OK, so I'm going to do a demo of the Jaeger UI. And we are going to use a mock application called Hot Rod to do this demo. So I'm just copying and pasting this command that just runs Jaeger in a Docker container in all-in-one mode. So it has integrated storage. So that is done. Let us go to... So the front end for Docker, not Docker, the front end for Jaeger is at localhost 16686. You have the Jaeger logo. And I'm going to do the same for the demo application. So here, we are launching the demo application called Hot Rod. So I would direct your attention towards the logs. So now when we look at these logs here, like you see the word service, with route, service front-end, service customer, and service driver. Now, these logs immediately tell us that this demo application consists of multiple smaller services. In this case, I think we are most interested in the front-end because the front-end is usually the entry point for these apps. So let me click on this address. So the front-end takes us to this particular website. Now, let me give you an introduction about Hot Rod. Hot Rod stands for Rides on Demand. And it is this simulation of a ride-sharing app, like, say, Uber or Didi, that allows customers to request vehicles for a given location. So we only support these 4 locations in this app. Now, when we click on one of these, you see it says it's dispatching an app, and then a car, and then here, we see this number, which is a New York-style number plate. It's a car number plate, and it says that it's arriving in some amount of time. So this application goes through, looks at the nearest cars, and sends one of these cars to the customer. Some of the things that are important to note in this site, we have this web client ID. Now, this is a unique ID that's given by the JavaScript on the front end. If I refresh this browser window, you'd see a different ID. And we have request IDs. So this is also by the front end. The latency as measured on the front end. Now that we've done this, we go to the Jaeger UI. Now, it's very interesting that we haven't really seen what this application is. So we know that this application consists of many parts, but we don't really know how these parts relate to each other, what the architecture is. Now, recall that we already did one request over here. Now, this sends data, span data, to Jaeger. So Jaeger captures that data, and it stores it and allows you to visualize it. So when you go to the Dependencies tab here, so we can already see that the front-end service calls 3 services, customer, driver, and route. And customer calls MySQL, backing store. Driver calls Redis. So already we are gaining an understanding of how these services communicate with each other. So we've only made one request. So let's go to the search page, and let's hit on Find Traces. So this shows 2 traces for this particular website, right, for this app. So on the front end, like we see that we called HTTP get/dispatch. That's the endpoint that front end called. And over here, it shows all the services involved in serving that request. And then we see that there are a few errors. And we also see this time. It says that it took about 750 milliseconds. And this, if you notice, is small. 750 is smaller than 759. And this is because this particular timing comes from the front end, whereas the timing over here, this 750, is coming from the back end. It's also collected today, a few minutes ago, so all of this is just an information screen, right? We also have this display here that shows like how much time this took. It's about 700 something milliseconds. Let us click into this. So when we click into this, we immediately get a timeline view. So over here we see that, we can just go through this. We see that there's this front-end service that calls a customer service, which calls MySQL. Once we collapse this, we see that the front-end service calls driver.findNearest. And then we see a get route being called many times. So if you look at this, this is just a timeline view saying we do not know what the business logic inside is, but we know how long each component took and how they interacted with each other. So this is very contextual information. This is all from one trace. It's collected across multiple services, and it's all presented to you in one screen. So it tells you a story of what's happening in your service architecture. Now, if you click into this, we see these logs, and these logs are very contextualized. These are per request logs. So looking at these logs, we can see that there's a HTTP request received, they was getting a customer, and then there's a search for the nearest drivers. And once that search is completed, the application finds the most efficient route. And once it's done, it finally sends the dispatch, which is sending a car to the customer. Now, we see all of this in this logging information. This is in contrast with the logs over here. Now, these are the same logs from all these services for just one request. And it is very difficult to make out what's going on from here, as opposed to looking at the trace view where everything is in context. Now, I'm going to dig deeper into this timeline to explore more interesting things. So we have this log over here. And when we go down, we see front-end calls customer, which calls MySQL. And then we see front-end calling the driver service, and the driver service calls Redis. One of the interesting things is you can annotate errors. So this exclamation mark over here means that there's an error in the span. And we can dig in to see what that error is. Like, we see that there's a Redis timeout. So it's very informational that way. And users can choose to report errors at any granularity that they want. We also have, for things like MySQL, you can actually put in the MySQL query right inside your span so that you know exactly what query was executing at that point. So going down, we might want to see how the performance of this app, or we might want to learn what is actually going on when someone calls a dispatch. Over here we see that driver calls Redis many times. And it's very easy to notice in this example that each of these calls only happens after the previous call completed. So here already you get some notion of a question that is, can these Redis calls be made in parallel? They're being made in serial right now, but do they have to be made in serial? And that is something that can be investigated. Looking at this front-end service, it also seems like 3 of these calls happen in parallel, and then the next 3, and then the next 3, and so on. So also this gives you, we can clearly see this pattern right here. And this also gives us this notion of whether they are resource constrained on some other resource, right? Maybe there's an executor pool with only 3 threads. And the trace timeline view gives you this nice visualization that allows you to dig in very deep into a single request and find out how that request is going on. The key point is all of this is empirical data. This is actual data that the app is sending to Jaeger. So let's go back to our simulation. Now I'm curious about how the simulation works when there are multiple requests. Right now we have only seen one request. So I'm going to click on something many times. So if you see the request ID, it's just increasing. So let me click some more. So we have a lot of requests. And if you see if you notice the latency, our initial request was only 759 milliseconds, and our final request is almost 3 seconds. So it is increasing. So clearly there's something funny going on with the app. So to see what's going on, I'm going to select one of these number plates, and going to the Jaeger UI, I'm going to search via tag. So on the left side, there's this search functionality. You can search via key value pairs. So it's just key equal to value, and then if your instrumentation tags it correctly, you could just get that particular result. So we see over here that this particular trace took 1.79 seconds. Let us dig into it. Now, going inside, this MySQL select is almost taking 1.39 seconds. And clearly something is wrong here, right? And the way you look at it is just go into this. You see that there's the select query. The select looks normal, but let's look into the logs. Now, the interesting thing here is we see that this particular log line says that it's waiting for a lock behind for transactions, right? And this happens, and the lock is acquired only after 1 whole second. Now, OpenTracing allows us to create rich instrumentation that exposes these details onto logs. And in this case, this could potentially be a database that's configured to only use one serial connection, or only one, or something behind the queue. So essentially, when there are multiple requests coming in, everything is waiting for the previous request to complete before it can be served. So ideally, the next step you take is look into what is going on here. The other interesting thing here is that you see these blockers. And these blockers are request IDs from this page. So these request IDs are available in the UI, and your app knows about it. And the interesting thing is your storage layer knows about it. The storage layer is, looking at the dependencies, the storage layer is 3 levels deep. It's the thing at the bottom. The bottommost thing knows who the customer that made this request. And this is possible through an OpenTracing feature called baggage, which allows you to pass key value pairs throughout your architecture without changing your application's APIs. So that is all I have for the demo. So I'm going to hand it back to Juan. I don't know where it went. Okay. No. No. No, it's not working.
Checking? Check. Okay, thank you. Okay, thanks. Let's see. Okay, sorry. Thanks, Prithvi, for the demo. So as you can probably tell by now, Jaeger is an open source, OpenTracing compatible distributed tracing system. So Jaeger was inspired by Google's Dapper and OpenZipkin, and was started at Uber in August 2015. We open sourced the project in April 2017, and it was accepted as an official CNCF member project in September 2017. So let's just take a brief look at the tech stack. The Jaeger backend is written in Golang, and we support pluggable storage engines such as Cassandra, Elasticsearch, and an in-memory storage to persist traces. The front end is written in JavaScript, and it uses the React framework. We support many different languages and have client support for all the languages listed on the bottom here. So one of the awesome things to note is that the PHP, the C#, and the Ruby Jaeger clients were all community contributed. So speaking of community, we have 10 full-time engineers at both Uber and Red Hat working on Jaeger. We have 60 contributors to the main Jaeger repository, but if we were to include all the sub-repositories like client libraries and such, then we would have a total of 200 plus contributors. We also have many organizations using Jaeger for day-to-day debugging, as listed here. If your organization is already using Jaeger in production, let us know and we'll gladly add you to the list. So let's just briefly summarize what distributed tracing is for. So firstly, rather than monitoring individual components of the architecture, like with metrics and logs, we can monitor distributed transactions across multiple components. Additionally, we can use traces to do root cause analysis, which is integral for companies like Uber, where each request will sometimes fan out to hundreds of different services. We can also use traces to detect the critical path and do performance and latency optimizations. So in the demo we saw previously, we saw that MySQL was taking the longest time. We could have gone in there and we could have tried to optimize that, as that was where the bottleneck was. Furthermore, with some post-processing, we can generate dependency diagrams that allow engineers to better understand the system that they're working on. And finally, distributed tracing provides a generic distributed context propagation facility upon which everything else is built. Okay, so these are some of the recent highlights for the Jaeger project. So I'm just going to gloss over them here. We have adaptive sampling, we have asynchronous ingestion, trace comparisons, and Jaeger operator. So we'll actually do a deeper dive into each one of these new features tomorrow during the deep dive session, since if I go over all of them today, none of you guys would show up tomorrow. So, okay, so let's take a brief look at the project roadmap. So as in the previous slide, I'm only just going to gloss over some of the new features here, and in the deep dive tomorrow, we'll go through and go through all the features. Okay, so one of the features I'd like to talk about is called post-trace sampling, and it's something that we're very interested in. So currently, Jaeger samples traces based on a default probability of 1 in 1,000. This means that if there are 1,000 requests, we expect there to be at least one request that is actually traced and sampled and saved in Jaeger. This means that we have a high probability of missing interesting and anomalous traces. With post-trace sampling, we'll sample all the requests and then cherry-pick only the interesting traces based on certain heuristics. These heuristics can be as simple as keeping a histogram of trace durations and then just cherry-picking the P1 and the P99 duration traces, or counting the number of errors in a single trace and only saving those that cross a certain threshold. So next we have the data pipeline. This is based on Kafka and Apache Flink, which is a stream processing system. The data pipeline allows us to support feature extraction, trace aggregations, and data mining. This is a huge feature because although individual traces are useful, as you saw in the demo, aggregations of traces allow us to build models that can be used to pinpoint anomalous traces and automatically surface them to the engineer. You just can't do that by looking at single traces in isolation. So another way of phrasing this is that single traces are single traces are reactively looked at by engineers only after they discover a problem. On the other hand, once you have aggregations of traces, you can automatically detect anomalies and then proactively let users know of degradations of their services. So a lot of this is already live at Uber, and we'll be open sourcing all of this shortly. So the last feature I'll touch upon is incomplete span support. So at the moment, spans are only emitted once when the service is finished with its work. However, some services have workflows that are hours long, which means that the users have zero observability into ongoing requests until the entire workflow is finished. So this new feature allows you to incrementally build spans and view them as the workflow is running, giving you greater insight into these longer workflows. So again, we'll go into a deeper dive into all of these topics tomorrow, but I just wanted to cover them here. Okay, and that's all we had. for today. Thanks for coming. So are there any questions I can answer? We can answer? Yep. Mm-hmm.
Make sure to repeat the question.
Thank you. When I use Jaeger query read log from Kafka, how index the log?
How do we index the log? Okay.
Yeah.
In Kafka, sorry?
In Kafka, Kafka.
How do we index the log in Kafka?
Yeah. Use the Jaeger query from the Kafka.
Mm-hmm.
I could take it.
Oh, yeah.
Yeah, so we do not index the code. I mean, we do not index logs, or we do not index anything in Kafka. So we only put things onto Kafka, and we use it as a buffer mechanism. So eventually, finally, it ends up in Cassandra or Elasticsearch. On Kafka itself, there's no indexing.
Is there a public Jaeger services in any of the cloud provider?
So the question asks is whether there's a hosted Jaeger service. So,
Yeah.
you want to pay someone money to just send
Yes.
fans. Yeah. I think there is. Yeah.
I don't think there is.
There is one. It might. Hold on. I will get back to you on this. There's at least one option.
Okay, thank you.
Yeah, like Alibaba, not Alibaba.
Okay, we can take questions after anyway.
Yeah, we're just going to hang out here, and you could just come and ask questions on the side.
So just one last slide. Our deep dive session is tomorrow. So if you were interested in any of the topics that I mentioned, it's in the same room here at 2:20, and we hope to see you there. And also, if you're interested in how other organizations are using OpenTracing, there is a talk that started at the same time as this talk and is ending right now. So if you have a time machine, you can go back and watch that as well. Okay, thank you.